For Chapter 7, which is really Unit 8 in our sequence here, we're going to be applying integrals for area and volume. So areas of certain regions in the plane can be calculated with definite integrals. We expect that you are able to evaluate a definite integral, either by using the antiderivative and subbing in A and B, fundamental theorem, or by using your calculator to assist, okay? But a lot of these that we're going to do, we're just going to focus on the setup, and then again, we expect your knowledge to be able to do this part of it to actually get the finite area. Today's video is going to focus on the area between curves that are perpendicular to the x-axis, so we're going to be painting vertically, if you will. All right, the graph above shows f of x equals 5x minus x squared and g of x equals x. Step 1, label each function. Well, f of x, I'm going to label in purple, is 5x minus x squared, which must be this parabola because of our x squared. I can double check. I've got a 0 at 0 and a 0 at 5, which is what would happen if you factored out the x here, so we're all good. Then g of x, oops, I was supposed to label that. F of x. G of x then being just the line x. Well, here's my line x, and this is g of x. Step 2, shade the region between f of x and g of x. So we have to have a finite area because we're shading something that is bounded and label it R. So it's got to touch the blue and the purple, and we will call this area R. Third part, write an integral expression. Well, an expression that has an integral so that we can find the area of region R. Well, I know I'm going to need an integral. It looks like I start these connecting at 0, and I end these, because I'm painting perpendicular to the x-axis, I end these at 4. Now, to be sure of that, how do we figure out where two functions are intersecting? We could set them equal to each other. So I'm going to subtract the x to the other side. I'm going to end up with 0 equals 4x minus x squared. 0 equals x times 4 minus x. X equals 0 and x equals 4. So those are my bounds of my integral. Okay. Remember, when you're given a graph, though, you can read straight from it, and that's totally fine. Then I need to think about how am I going to find this yellow area? Well, I can find the area of all of what's under the purple minus all of what's under the blue. So I'm going to take the integral of f of x minus the integral of g of x, and because I'm subtracting, I can put those into the same integral, and I end up with f of x minus g of x. More specifically then, from 0 until 4 of 5x minus x squared minus x dx, and I could find that antiderivative and find that actual area. Notice, though, this says just write the integral expression that would find the area. We don't actually need to find the numerical value. All right, the graph above shows f of x and g of x. Write an integral expression that would find the area. So again, thinking about the area, I could find the area all under this purple, right? We know how to find that, minus everything that's under this orange one. Okay, well, I'm going to integrate from this value, 5 minus the square root of 7 over 2, until this value, 5 plus the square root of 7 over 2. My big area is going to be my purple function, which is g of x, minus my orange area, this bottom area, which is f of x. Putting that all together then, if I actually replace, oh, just kidding, I don't have an equation to replace those functions. They're just called g and f. So what I'm doing is I'm taking the area found by this purple minus the area found by the orange. And it leaves me with this paint stroke, if you will. If I look back at this one, I found the area underneath all of the purple. Then I had the area under the blue. I subtracted those, and it left me with this paint stroke. Well, that paint stroke represents f of x minus g of x, right? Top function minus bottom function. Top function minus bottom function. G of x minus f of x. So that's how we get to our general find the area under the curve and above the x-axis, okay? So keeping everything in positivity right now, we know that the integral will take care of itself if it ends up being somewhere else. If we have two curves, f of x and g of x, with f of x being greater than, so this is like the top function and g of x would be the bottom function, then the area bounded by the vertical lines x equals a and x equals b is represented by the integral from a to b of top minus bottom when talking about painting down to the x-axis. So again, this would be like our top purple function minus our bottom blue function, and you're left with this paint stroke, top minus bottom, top minus bottom, top minus bottom. How many of those are you summing up? You're summing up an infinite amount of them. So thinking about that from a function standpoint, clear off all my colors here, we would be integrating from a to b of y equals f of x minus y equals g of x with respect to the x-axis. Because again, if we think about those as paint strokes, they have a width that's infinitesimally small and a height that is the difference between your y's, right? Your change in y is equal to f of x minus g of x. So each one of those paint strokes is really a representative rectangle from a Riemann sum. This is delta x and this is delta y, and we're finding the area of each one of those, summing up an infinite amount of them. All right, so I'm going to have you pause the video and try to write the integral expression to find the area of each shaded region. So I'm going to say again, it helps to think about top minus bottom, top minus bottom, top minus bottom. So go ahead and pause your video. See if you can write the integral expression for each one of these. Pause now. All right, let's check them out. So if I think about one representative rectangle, top minus bottom, I get purple minus blue. Here, top minus bottom, I get purple minus blue. And I chose to use their real names, okay? And then I was going from 1 to 3. Here, top minus bottom, blue minus purple. A and B, you would find them by finding where you intersect. This next one, hopefully you noticed we have two different areas. So this first area, top minus bottom, is red minus blue, but then we switch and this yellow area would be blue minus red. What do I want to do with the green area and the yellow area? I want to add them together. So I'm going to find the area of the first one plus the area of the second one, and then my top minus bottom just switches. So when we dip into other quadrants, we want to still think about top minus bottom. Another way that some students like to think about this is upper minus lower. Really what's happening though is this is greater minus lesser. Okay, so the bigger function minus the smaller function, right? Greater and lesser in terms of mathematics. All right, there is a mistake on my notes. I don't know if it's in your notes packet or not, but this should be x squared minus 6x plus 5. Double checking from last year. Yes. Okay, minus 6x plus 5. So we're supposed to find the exact value of a and then set up the integrals to find the total shaded area. Well, a is going to be where our two functions intersect. So find a. We're going to set these two equal to each other. And again, it's x squared minus 6x plus 5. Then I add my x squared over, subtract my 4x, I get 2x squared minus 10x plus 5. This is not going to be able to factor, so I'm going to use the quadratic formula. X equals opposite b plus or minus square root b squared minus 4ac divided by 2a. Let me get x equals 10 plus or minus the square root of 4 times 2 is 8 times 5 is 40. 100 minus 40 is 60. Square root of 60 is going to be 2 root 15 all over 4. We can take out a 2 from each of those. X equals 5 plus or minus the square root of 15 over 2. Well, thinking about this, we've got the plus and the minus. If I were to extend these out, these parabolas, this a is going to be the x minus 5 minus the square root of 15 over 2. So nice little throwback to AAA there for you. We're supposed to then set up the integral to find the total shaded area. Remember, here we have two areas. If I paint up and down, I have this green area and I have this yellow area. And when I find the green area, I'm going to sum between 0 and a of top, which is g of x, minus f of x with respect to x. Then I'm going to add to that from 5 minus the square root of 15 over 2 until 1, my new top minus bottom, which is f of x minus g of x. Now, because we're just setting this up, you can leave these called f and g. You don't have to sub in their mathematical expressions. Could you? Sure. But on a free response question, it's going to save you some time if you just write g and f as opposed to writing in the full functions. Okay, now comes time to actually find the exact area, all right? So I'm going to have you find the find the bounds so we can get started with our setup. So we're going to set our functions equal to each other, figure out our a and our b, and try the integral setup. Pause your video and then come back and compare. All right, so checking in with you. Work to find the bounds, set these two things equal. This one factors nicely, all right? So we get x equals -1 and x equals 3. Looking at my graph, f of x is my top function, it's the parabola. G of x is my bottom function, it's the line. So f of x minus g of x. This would be an okay answer. This is also an okay answer. This is also an okay answer, all right? All of those work to represent the integral setup, finding that area. So the last thing about this one that's a little different is that this actually asks us to find that area. Well, in your calculator, you could just do a nice little f int, okay? But I want you to challenge yourself and try to take the antiderivative and then top minus bottom, right? So f of b minus f of a, okay? So pause your video, take this antiderivative, evaluate at 3, evaluate at -1, see if you can get the area of the shaded region without using f int. Go. Well, pause, but go. All right, so remember to do an integral. You take the antiderivative of each piece, and then you sub in the top number minus subbing in the bottom number. Math, fractions, love it, no calculator. 32/3 is going to be our final answer. All right, so what if instead of painting up and down, we painted side to side? Well, painting up and down, we go from A to B, which are x values, right? And we have f of x minus g of x, right? Or g of x minus f of x, but top minus bottom. And then we end up with widths that are dx, infinitesimally small, because we're painting from here to here, right? And so this part is dx, which is infinitesimally small. This part is our change in y of top minus bottom, if that's a function or if it's the x-axis, whatever it might be. So predict for yourself, what would change if we painted side to side? So instead of painting up and down, we painted side to side. Think about those rectangles. Okay, I would make sure that you have a good handle on this. This is your big summary. Upper minus lower, greater minus lesser, top minus bottom. Draw in that representative paint stroke every time. It'll help you a lot.